this video, we're going to look at the arc length and curvature of vector-valued functions. So we want to know how long of a path a particle or an item or an object traveled during some time interval in 3 space. So what we want is the arc length in 3 space. Now, if we think about what we did back in section 1.3, we found the arc length of a parametric equation, the arc length s, from t1 to t2 as the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. We're going to do something similar for our vectored valued functions in which we have f of t, g of t, and h of t. These are the equations we get from this theorem. So if I have only the I and j component, then it's going to be the derivative of my I component squared, the derivative of my g component squared, or my j component, I should say, squared from a to b, which is the modulus of the derivative of my vectored valued function. If we're in 3 space, then we just extend it out to 3 space. So let's take a look at our first example. We're going to find the arc length over this given interval. So let me just scroll this up so I can give myself some space. Because the function is a vectored value function, we're going to use this equation, which means first of all we need to find the derivative. So the first thing we're going to do is find f prime, excuse me, I don't know why I'm going to do f. I love f. F was my friend. R of t, so I'm going to do my derivative. And somebody asked me why I'm in I, j, and k. Well, I won't be. Let's go ahead and put it in the component form just because I can. And so I end up with 2t and then comma, the derivative of the second component is going to be 4t. So after I find my derivative, the second thing I'm going to do is find the modulus. So r of t, boom, boom, is equal to the square root of 2t, the quantity squared, plus 4t, the quantity squared, which gives me the square root of 4t squared plus 16t squared, which gives me 2 root 5, and then multiplied by t, because I end up with 20t squared underneath the square root, and so I end up with 2 the square root of 5t. So my arc length s is going to be the integration from 1 to 3 of 2 root 5 t dt, which gives me, let me see, the square root of 5t squared from 1 to 3, square root of 5 of 3 squared minus 1 squared, the square root of 5, and 9 minus 1 is 8. So my final answer is 8 root 5. Bam. Not too bad, really. Of all the things that we have done in the past, this could be considerably worse. Let's take a look at my next example. Again, the first thing I want to do is find my derivative, r of t. Did you see that r? That's an r. They wanted to be an f, but I saved it into an r. So this is going to be 2 cosine t. That's my first component. My second component is 5, and then my third component is negative 2 sine of t. Second thing I'm going to do is find the modulus of my r prime of t, which is going to be the square root of 4 cosine squared of t plus 5 squared. Look at that. Dun, dun, dun. And then I have a 4 cosine squared. I'm so proud of myself, but I had to erase. Sine squared of t. Now, remember that I can bring these two together, and if I have 4 the cosine squared of t plus 4 the sine squared of t, if I factor out a 4, I have cosine squared of t plus sine squared of t, but this thing is equal to 1, so this is just 4. It's a really ugly way of saying 4, so what I really have is 4 plus 25, which gives me the square root of 29. So even though it looked nasty, it really wasn't that bad. So the third thing I'm going to do is do s is equal to, I'm going to go from 0 to pi of the square root of 29 dt, which is just going to be the square root of 29 times t from 0 to pi, which gives me just 20 square root 29 times pi. And that is my final answer. So far, this isn't too bad. There are times when we're going to want to reparameterize. And so let's take a look at what happens when we're talking about reparameterizing. What does that do? So say we've got this vector valued function from s of t from a to t, where a is my starting point and I'm going to end at some value t. And it's slightly different than we did here. And so we have this, the square root of f prime of u squared, g prime of u squared, and h prime of u squared du. And the reason we're using u is to distinguish it between the time and the variable of the integration. So that's why we're just kind of introducing this dummy variable just to make it easier for us. So then s prime of t is the derivative of this integral, which of course this integral is the modulus of the vector valued function derivative of u du, which is just going to give us r prime of u of t. So if we assume that r of t defines a smooth curve, then the arc length is always increasing. So s prime of t is greater than 0 for t greater than a. So if r of t is a curve on which this modulus is equal to 1, then for all t, then we get this. We have that t represents the arc length as long as we start at 0. What this does is allow us to reparameterize functions to make them easier and sometimes more useful. So we have this arc length function. Now, the arc length now is a function rather than just a value. And so if I want to find the arc length parameterization of this, then the first thing I'm going to do is find the derivative, so that doesn't change. So r prime of t, this is going to be equal to -3 sine of t, comma, 3 cosine of t, comma, and then of course 4. And now I'm going to set this up so that I have s of t is equal to from 0 to t, and that's because this is my a, and if you look up my formula up above, my lower bound is a. In this case, my a happens to be 0. And then I'm going to have the square root of, and now instead of having t, I'm going to use u. So I have -3, the sine of u, the quantity squared, plus 3, the cosine of u, the quantity squared, plus 4 squared du. Now this is going to be similar to my previous one. We know that this is going to give me 9, the sine squared of u, plus 9, the cosine squared of u. So we know that this ends up becoming just 9. So what this really then is from 0 to t of the square root of 9 plus 16 du, which is just equal to from 0 to t of square root of 25, which is 5 du, which is 5t from 0, 5u, not t, 5u from 0 to t, which is just 5t. Cool. So that tells me that my s parameter is equal to 5t. That means that t must be equal to s divided by 5. So what I'm going to do is replace r of t with r of s, which gives me my original function, which was 3 the cosine of t becomes 3 the cosine of s divided by 5, comma, and then I have 3, the sine of it was t is now s divided by 5, and then my last one, which was 4t t becomes 4 over 5s, and I just need to use the correct bracket. And so there is my final answer. Not too bad. Let's talk about curvature. So curvature is how sharp of a turn we have on our graph. So if this represents a road and you're driving along the road, this turn, say this road is like, oh, I don't know, 60 miles an hour. This turn would slow down to probably about 50. This one would slow down to probably about 40. This one would probably slow down to about 25. And this one would probably slow down to about, I don't know, 35. And that's because this is less curved. This is a curvature that is has less of a curve than, say, this one. So the sharper the turn in the graph, the greater the curvature, which means the smaller the radius. So it's like a reciprocal kind of thing going on. So the greater the curvature, so the greater the number when we find our curvature number, the bigger it is, that is the smaller the circle it is in here. So that it's more of a sharper turn. So I think this one might be a sharper turn than this one. Like I said, probably about a 25 mile an hour turn. And this one's probably about 35. This one's probably about 50, about 40, if the road represents a road that you get to go 60 on. So what we have is, let C be a smooth curve on the space given by R of S, where S is the arc length parameter, which is why we spent the other time just a few minutes ago. Then the curvature K at S is dt ds, which is t prime of S. Okay, this is an S, but we're mostly in T. Well, remember from 3.2 we have this. Our T of T, this is our unit vector, the tangent unit vector, is equal to the tangent vector divided by its modulus, but we want this in terms of S. So we need to find a unit tangent vector S for the function R of S, and then take the derivative, which is tedious. Fortunately, dun dun dun, we have these equations. We have our curvature, which is our unit tangent vector divided by our modulus of our tangent vector. And if we're in 3 space, boom, this is what we do for 3 space. We do the modulus of the derivative of the cross product and the second derivative of our vector divided by the modulus of our derivative, our tangent vector, cubed. If we have the graph of y is equal to f of x, and both x, y prime and double y prime exist, so the first and second derivative both exist, then the curvature at some given point is given by this lovely equation. So that's a little bit easier to digest than this. If we're asked to find the curvature for the given vector-valued function, then the first thing we need to do, because we're going to be using this formula, because I don't want to mess with this formula, is I'm going to find my first derivative and my second derivative, and I need to do the cross product of those two. So the first thing I'm going to do is find r prime of t. Notice I did an r there, not an f. I really wanted to do an r. Now this, of course, is t, 6t squared, and 4t. So my first derivative is 1, 12t, and 4. My second derivative, I almost made that into an f. My second derivative is going to be 0, 12, and 0. So now I'm going to do the cross product of r prime of t and r double prime of t. So I, j, k, my r prime is 1, 12t, and 4. My r double prime is 0, 12, and 0. So this is going to be kind of nice. So this is going to be equal to, that's what this is equal to. This is going to be I, and then I hat, so I don't lose it. And then I have 12t times 0, and then 12 times 4. So it's going to be 0 minus 36. And then plus, or excuse me, minus, because they're in the j. And then the j is going to be 0, and then 0 minus 0. Oh, that's kind of nice. And then plus j hat, and then plus k, and then k hat. Don't lose my hats. I have 12 times 1, and then minus 0. And so I have negative 36 in the I direction, and then nothing in the j direction. So I can put plus 0 in the j direction if I'm inclined, and then plus 12 in the k direction. And helps if I multiply right. 4 times 12 is not 36. 4 times 12 is 48. 48. What was I thinking? Craziness. Okay, so now I have to find the modulus of this. So I'm going to do the modulus of r prime of t crossed with r double prime of t, which is going to give me the square root of negative 48, the quantity squared, plus 0 squared, which doesn't give me anything, plus 12 squared. And this is going to end up giving me 12 root 17. That's what it simplifies to. Okay, so we found the numerator. It took all of that time. So our first step was find the first derivatives. Our second step was to do the cross product. The third step was to find that modulus. The fourth step is I do need to find the modulus of my first derivative. So I need to find my r prime of t, which is going to be the square root of 1 squared plus 12t squared plus 4 squared, which is going to give me the square root of, looks like 17 plus 144t squared. Okay, after I have found that, I now need to raise this to the third power. And I'm going to use my rules of exponents that says if I have the nth root of a raised to the m power, this is the nth root of a raised to the m power, which is the same thing as a raised to the m over n. So this is going to be equal to 17 plus 144t raised to the 3 over 2. All right, now I've found all of my pieces, and my last step, step number 5, is bringing them all together. It is the magnitude or the modulus of my cross product. So that was 12 root 17 divided by the 17 plus 144t squared. I dropped my squared, raised to the 3 over 2. And that is my curvature k of t. And I would have to find a value for t to tell you exactly how tight of a corner it is. I'd have to know it sometime. But that it is, this is generically, so this gives the curvature k. And the k is it's actually not a regular k, it's a Greek letter k. So it's, I'm not going to draw it well, so it's going to be just a k. But really isn't. That little k is like kappa. It's not just k, just so you know. Okay, let's take a look at my next example. First thing I want to do again is find my first and second derivative, so r prime of t, which is going to give me 2 cosine of t, and then 5, and then negative 2 sine of t. Now I'm going to do my second derivative, which is going to give me negative 2 sine of t, 0, and negative 2 cosine of t. Second thing I'm going to do is my cross product. So r prime of t crossed with r double prime of t. So this is going to be equal to I, j, and k. 2 cosine of t, 5 negative 2 sine of t, negative 2 sine of t, 0, and negative 2 cosine of t. And we get this to be, when we get done, negative 10 cosine of t in the I direction, plus 4 in the j direction, plus 10 the sine of t in the k direction. Now its modulus, so that's my third step. Let's do it in a different color. Let's do it in blue. So we have r prime of t crossed with r double prime of t, and this is going to be equal to the square root of negative 10 cosine of t squared plus 4 squared plus 10 the sine of t squared. And you're thinking, wow, this looks vaguely familiar, and it most certainly does. We'll end up with the sine squareds and the cosine squareds getting to become 1, and so we end up with 2 to the square root of 29. So that actually is pretty nice. Now, my next step, if you remember, my next step is to take the modulus of the, or the norm of the first derivative. So let's go back and do step number 4 here. Step number 4 is going to be the modulus of r prime of t, the norm, the magnitude. I keep calling it the modulus, and I keep thinking of complex. So we're not in complex. Let's not go with complex. So it is, every time I'm saying the modulus, I should be saying the magnitude or the norm. So just want to make that clear. I just love the modulus. It just sounds nice. It is the magnitude or the norm is what I'm doing. Modulus is when we're talking about complex numbers. I don't know where I got that in my head. Anyways, back to this. This is going to be the square root of. Now I found my derivative, and so this is going to be 2 the cosine of t, the quantity squared, and then it's going to be plus 5 squared, and then plus negative 2 the sine of t squared. And we know at this point that are my sine squareds and my cosine squareds are going to become 1. This should be feeling comfortable at this point. So this is going to give us the square root of 29. And once again, we are raising it to the third power. This whole time I was raising it to the third power, raising this to the third power, which gives me 29 raised to the 3 divided by 2. Okay. So now I go back to my formula, and remember my formula is the magnitude of the cross product divided by the cube of the magnitude of r prime. So what I have then, my final answer, my k value, is going to be equal to 2 the square root of 29 over 29 raised to the 3 over 2, which we know based on the fact that it's 29 raised to the 1/2 in the numerator, this is going to give me just 2 over 29 because I'm using the rules of exponents. If I have a raised to the 1/2 divided by a raised to the 3/2, this becomes 1 over a raised to the 1. Or, yeah, because it'll be 2 over 2, which is 1. All right, so that's my answer. Now, that's not a very big, that actually is not a very big k value, which means that it's not a very big, it's not a very tight corner. Just something to think about. Okay, now this one I want to know the curvature at a particular point. So I've got to figure out what t value is going to give me that point, and that point has to be on the curve. So what I know is that the square root of 2t has to equal 0. These have to be equivalent. I have e to the t has to equal 1. These two have to be equivalent. And I have e raised to the negative t has to equal 1. because these have to be equivalent. Now, the reason I'm going through this is because I need to find that value of t, because I'll need to evaluate this at some given t value. I can go through the whole process like I did before and then do this last, but let's just do this right out of the gate. So the only way this holds true is if t is equal to 0. That's the only way. E raised to something is 1 only when that e raised to that something is 0. Same thing here. And then it works for this one. So e raised to the 0 is 1. That's the only time we have e is equal to 1. If I have e raised to some power, that power has to equal 0. And so that holds for that one. So now I've got where it happens. So let's go ahead and go through our steps. So step number 1 is I'm going to do r prime of t, which is going to give me the square root of 2, e to the t all day long, and negative e to the negative t all day long. Now, because you all love your t's all day long, let's see what happens when I do r prime of 0. So I can do this right out of the gate. That means I don't have to actually do, when I still have to do all the process, right? But it helps it because I'm now a all-numeric and I don't see t anywhere. So if I put r prime of 0, it doesn't change my first one. It's still the square root of 2 because I can't put that in there. But e to the 0 is 1, and negative e raised to the negative 0 is negative 1. So now when I do the cross product, I get to use those instead of the square root of 2, e to the t, and negative e to the t. I still have to find r double prime of t, which is going to give me the derivative of the constant is 0. E to the t is still e to the t all day long, and this becomes e raised to the negative t. R double prime of 0, see I wanted to do an f there, is going to be equal to 0, 1, and 1. So I've started you out, and I want you to go ahead and finish this off. The only thing that we did that I wanted to start you out with is we had to figure out what the evaluation of t is. I was either going to have to do it now or I was going to have to do it later. I could have totally done all the steps as I did before and then find the value of t and then evaluated my curvature function when I got done. It's a function of t. I could have done that at the last and then, evaluated at whatever my t value is. But this allows me to avoid using E of t stuff. So I'm going to go ahead and let you finish it. So I'm going to put this on pause. I want you all to pause and then get an answer. Welcome back. Hopefully you found your curvature evaluate at t is equal to 0 as being the square root of 2 over 4 as your final answer. Okay, so when we're looking at vectors, there are two other vectors besides the tangent vector or the unit tangent vector. It doesn't matter, just the tangent vector or the unit tangent. Two other vectors that we want to talk about. One is the principal unit normal vector and the binomial vector. A couple of things to note. The binomial vector is always orthogonal to both the unit tangent vector and the normal vector. And my binomial vector b of t is always by default a unit vector. So our unit normal vector, BAM, is given as the derivative of our tangent unit vector divided by the norm or the magnitude of the tangent vector, the unit tangent vector. And then the binomial vector is defined as the cross product of the unit tangent vector and the normal vector. Okay, cool. Now, the principal unit normal vector is a little challenging to calculate because the unit tangent vector involves a quotient, and this quotient typically will have a square root in the denominator. In three-dimensional, we are finding the cross product of the unit tangent vector and the unit normal vector, which can be even more cumbersome. So if we can just hold off, we'll find in 3.4 we have some pretty good formulas for doing all of the shenanigans you'd have to do in those steps, those in-between steps. So if we can wait until we get into the next section, we're going to get some pretty awesome formulas for those. So let's start out with finding the unit tangent vector. Just as a reminder, this is what we were doing in our last video, and then the unit normal vector at t equals 0 for the plane curve given below. So the first thing we're going to do is find our tangent unit vector, which we know that t of little t is equal to the derivative of my original vector divided by its, I want to say modulus, but it is not. It is the magnitude, r of t. R of t, let me erase r of t. Okay, so what we have, we're going to find r prime of t, which is going to give me 3t squared minus 4, and then 10t squared. Okay, and now I'm going to find that, and I want to do the prime there. I'm going to find the magnitude, r prime of t magnitude, which is equal to the square root of 3t squared minus 4, the quantity squared, plus 10t, the quantity squared, which is going to give me 9t squared plus 96t cubed plus 16 when I get done with all of the multiplications. That should be 9t to the 4th, excuse me, that should be to the 4th power. And now I'm going to evaluate it at 0. So r prime of 0, which is going to give me just the square root of 16, which is just 4. And r prime of 0 is just going to give me negative 4 and 0. So then the tangent unit vector evaluated at 0 is going to be the negative 4 and 0 divided by 4, which gets me negative 1 and 0. So there is my unit tangent vector at t is equal to 0. So that's my first part. Bam. Now this is kind of cheesy. And the reason this is kind of cheesy is that the unit normal vector, now if I were to graph this on the xy plane, it represents this vector. This is the vector negative 1 comma 0. So a vector that is normal to this would be either this vector, which is 0 comma 1, or it could be this vector, which is 0 comma negative 1. And then of course those would be normal to each other. So it was kind of a cheesy one because I ended up with my tangent unit vector being on the x-axis. So there is that. Okay, so here's some takeaways from where we are. The normal vector and the binomial vector, those together form a plane that is perpendicular to the curve at any point on the curve, and we call that the normal plane. So the unit normal vector and the binomial vector, that's this and this, are called, when I put those together, it produces the normal plane. All three of them together, the tangent, the normal, and the binomial unit vectors, form a frame of reference in three-dimensional space called the free net frame of reference, also called TNB frame. That's this. So this gives us a frame of reference with all three of the vectors, and that gives us a frame of reference. The tangent and the normal unit vectors form the osculating plane of C at the point P on the curve. Sorry about that. My cat was getting sick, and as you know, as a pet parent or a parent When you hear someone getting sick or something getting sick, you stop everything to find out what's going on to prevent it from, going everywhere. So anyways, let's move on. We're now going to look at the radius of curvature and the osculating circle. So suppose we form a circle of the osculating plane of C at point P on the curvature. Assume that the circle has the same curvature as the curve does at point P. Let the circles have radius r. Then the curvature of the circle is given 1 over r. We call r the radius of curvature and is equal to the reciprocal of their curvature. So in other words, my radius of curvature is 1 over my curvature. That's my radius of curvature. And if the circle lies on the concave side of the curve and is tangent to the curve at the point P, then we call this circle the osculating circle of C at point P, as shown below. All right. So find the radius of curvature at this point. And we'll look at the osculating plane in a moment, but first we're going to find the radius of curvature. Now, if you remember, this one has a slightly different formula. K kappa of x is equal to y double prime of x, my function, which is what this is, of x, divided by 1 plus y prime of x, the quantity squared, and then raised to the 3 over 2. So this one isn't going to be as interesting, potentially, maybe interesting, we don't know. So let's go ahead and start with the derivative. So first thing I'm going to do in this case is find y prime of x. So that is going to be 1 over x plus 1 multiplied by the derivative of x plus 1, which is just 1. So then y double prime of x, well, I'm going to come over here to make my life easy, and I'm going to write this as x plus 1 raised to the negative 1, so I can use the power rule and the chain rule, so I get negative, and then I have x plus 1 raised to the negative 2. Okay, so now I'm going to go ahead and put everything in the right places. So this is going to be equal to, I have negative 1 over x plus 1 raised to the 2. So that is my y double prime of x. And then in the denominator, I'm going to have 1 plus, and then I'm going to have 1 over 1 plus x, the quantity squared. This is going to be raised to the 3 over 2. Now, I could clean this up if I was asked to find the radius of curvature, not at a particular point. But because they're asking for me to find this at a particular point, I'm going to go ahead and find k of 2. This is my x value. This is my y value, but I don't actually need that for this. They're just telling you that that would have been the y value. So I'm going to go ahead and put 2 in, and so I'm going to have negative 1 over, and this is going to be 2 plus 1, so it's going to be 3 squared. And then in the denominator, I'm going to have 1 plus 1 over, and then I have 1 plus, so I have 2 plus, so it's 3 squared again, raised to the 3 over 2. So this is going to equal to negative 1 over 9. And then in the denominator, I'm going to end up with, let me see, this is going to give me 1/9 plus 1 is 10/9. Is that right? 10/9, yep. 10/9 raised to the 3 over 2. Which is the same thing as negative 1/9 multiplied by 9 over 10 raised to the 3 over 2. So that gives me, let me see, 3 over the 10 root 10, which I guess could be wrote, if we're inclined, as 3 root 10 over 100. I'm not sure if that really helped us anything. Radius of curvature is 1 over k evaluated at 2. And so I end up with 10 root 10 over 3. I'm going to leave it like that. So there's my final answer. Let's take a look at this one. We find the equation of the normal plane and the osculating plane of the curve at that given point. So the first thing we're going to do is figure out what the t value is, just like I did before. So I know that this has to equal this, this has to equal this, and this middle term I almost left out has to equal this. Oh, well, that's nice. That tells me that t is equal to pi, that middle one. Oh, so I know what my t is. That's kind of nice. Okay, so now let's go ahead and differentiate twice. So r prime of t is going to give us, I have 3, so 6, the cosine of 3t, and then I have 1, and then I'll have negative 6, the sine of 3t, and I might as well evaluate it because I'm here. So let's go ahead and evaluate this. So r prime of pi, which is going to give me the cosine of 3 pi, which is negative 6, and then 1, and then 0. That's nice. We always like that. So then the modulus, or the magnitude, is going to be the square root of negative 6 squared plus 1 squared plus 0 squared, which gives me the square root of 37. And then I'm going to do r double prime. So r double prime of t, which gives me, let me see, 18, the negative sign 18 of 3t, and then 0, and then negative 18 of the cosine of 3t. R double prime evaluated at pi is going to give me 0, 0. Ooh, that's nice. And then 18. So that's really nice. So I've found my modulus. And I know at some point I'm going to have to cube this. I kind of did this one out of order because I just got so excited. Okay, so I need to find the cross product of these two. So that is my second step. So I'm going to find the cross product of r prime of pi crossed with r double prime of pi, which is going to give me the I, j, and k. And I can use these negative 6, 1, and 0, 0, and 18. This gives me, when I get done, this should give me 18, 108, and 0. So then I'm going to then find the magnitude. Which is going to give me the square root of 18 squared plus 108 squared plus 0 squared, which gives me 18 the square root of 37. Oh, that's kind of nice. I get kind of excited when I start to see that stuff. So my binomial vector, evaluated at t, is going to give me my r prime of pi crossed with r double prime of pi, which we found, divided by the magnitude of the cross product of these two, pi, and we want to do pi there. Should have pi everywhere. Pi here, pi there, everywhere, a pi, pi. That's pi. That's pi. Bam. So we end up with the cross product, which was, that was when I did the cross product, I got 18 and 108 and 0 divided by 18 root 37, which, believe it or not, does reduce. It reduces to, let me see, 1 over the square root of 37 will stay out, and I'll end up with 1, 6, and 0. So that is my binormal vector. And then I'm going to find my unit vector, my unit tangent vector of pi, which is r prime of pi divided by the magnitude of r prime of pi. Oh, I guess I did not need that raised to the third power, so let me get rid of that. Bam. Okay. It's not something I needed, so going back here, which is going to be equal to, we have the r prime of t, which was -1, or -6, 1, and 0. So -6, 1, and 0, divided by its magnitude, which was the square root of 37, which gives me 1 over the square root of 37 multiplied by -6, 1, and 0. And there is my unit tangent vector and my binormal vector. Okay. Now we've got to bring into the plane that happens here. Now, if we remember, I believe it's 2.7, that we know the equation of the plane passing through the point. So the plane passing through the point x naught, y naught, and z naught is given as the a x minus x naught plus b y minus y naught plus c z minus z naught is equal to 0. And you're thinking, well, where did this A, B, C shenanigans come from? Well, A, B, and C are the normal vector. Do you remember from the plane? So my A, B, and C is going to come from my normal vector. So my normal vector is going to be this one. So I have my A is equal to -6, my B is equal to 1, and my C is equal to 0. And if you remember the point that we had when we started out with, the point 0, pi, and -2. So this is the point 0, pi, and -2. So my equation of my plane that is normal is going to be -6 x minus 0 plus 1 y minus pi plus 0 and then z minus -2 is equal to 0. And so I have -6x plus y minus pi is equal to 0. So my equation is y. Let's go ahead and solve for y. I don't have to. I can leave it like this. I have -6x plus y is equal to pi. If I wanted to solve for y, I'd get y is equal to 6x plus pi if I was so inclined. And then we have to do it again for my other vector. So my other vector, when I have my a, b, and c, a, b, and c, my other one is my other vector, which, if you remember, is the 1, 6, and 0. So a is 1, b is 6, and c is 0. And this is for the oculating plane of the given curve, because this has the normal vector. So we do the same thing. We still have the same points, and so it's going to be, for this one, it's going to be 1, and then x minus 0, still the same point, plus 6y minus pi, still the same point, plus 0, still z is still 0, z plus 2 is equal to 0, And so I get my other equation, which is x plus 6y is equal to 6 pi. And so here's my first part. In fact, I'll probably leave it like this. And here is my second part. So these two equations in the xy plane, these two lines, are describing the oculating, that's what we started out with, the oculating plane of the curve. So we had to do a bunch of work to get there. Okay, here's my last problem where I'm looking for the particle moves along the plane curve described by this. Find the curvature as t increases from 0 to 2. So the first thing I'm going to do is find my curvature. I'm going to do that by find r prime of t. R prime of t is going to be 1 comma 2t. R double prime of t, just see that was sneaky. It's going to be 0 and 2. So that doesn't surprise us. Now I need to find my my cross product. So r prime of t crossed with r prime double prime of t, which is going to give me I, j, and k, 1, 2, t, 0. I don't have a k, so I'm going to put a 0 in. 0, 2, and 0, which is going to, when I get done, this is going to be 0, that's going to be 0, and I am just left with just 2k in the k direction. So the norm of this, or the magnitude of this cross product, is just going to be the square root of 2 squared, which is just, well, 2. All right. So let's go ahead and put that into, so I'll put that into my k of t, which is going to be my 2 divided by 1 plus 4t squared raised to the 3 over 2. Now let's take the derivative of this. So k prime of t is going to be, well, this is going to give me negative, I'm going to rewrite this as 2 multiplied by 1 plus 4t squared raised to the 3 divided by 2. And this should give me 24t, a negative 24t over 1 plus 4t squared raised to the, let me see, I'm going to take 1 away, so that's 5 halves, excuse me, 5 halves. Okay, so this is going to be negative. So k prime of t is going to be less than 0 for all t less than infinity, greater than 0 or less than infinity. So because this is negative, we are decreasing. So the curvature of k, the k of t, is decreasing when t is increasing from 0 to 2. So that's it. Now let's confirm this by actually putting in my t value at t equals 0 and t equals 1, and then maybe even t equals 2. So k, no, I didn't have to do all of this, right? It didn't ask for that. It just asked for, if we look at there, we wanted to know, find the curvature as t increases. So I didn't have to do the derivative part. The only reason I did that is because I wanted to see whether or not I expected it to increase or decrease. I didn't have to do that part. So I'm going to do k of 0, which is going to give me just 2. And then I'm going to do k of 1, just so we can see whether or not this truly is decreasing. And I'm going to get 2 over, and I put 1 in there, so I have the square root of 5 cubed, so 5 root 5. So it looks like it is decreasing. and then k is equal to 2. So that's going to be 2 over, and then it's going to be 16, one more, 17. 17 raised to the 3 over 2 is 17 root 17. So you can see that it is truly as t increases that my curvature is decreasing. So there you have it. That's it. That's it for today.